Everybody, welcome to my basement. Exciting. That's my arcade machine that I don't have time to play anymore since I have a daughter. so, what I want to get into today is basically all the basics of the periodic table. So we have to jot down a few notes for what's going on. Hopefully you did the vocab already, because knowing the terms beforehand, knowing what you're getting yourself into, definitely makes this much easier. So as we go through, we're going to be talking about things called like cations, anions. We're going to look at noble gases, alkali metals, different ions, different charges. And those are all in the vocab. So take 20, 25 minutes, work through that, and then make sure we pop into this. So I wanted to first revisit the trends from a few days ago. If you didn't finish the trends document, you have to, okay? Everything in chemistry happens in the order it does for a reason. So you need, again, I'm going to use a cliche. You have to learn to crawl before you can walk. You have to learn to walk before you can run. You can't just start sprinting when you're a year old. Okay, you just can't do it. So if you're skipping the last few lessons, like when I was gone, if you were skipping the last few and you're into today, you're going to have no clue what's going on because you didn't go through some of the electron things and some of the trends as well. So definitely finish that trends document. Make sure you have those definitions down. They are in this vocab also, but just make sure you're familiar with what we're getting into. Okay, the three trends we focused on. You can check my screen here. The first one was the atomic radius. So on the p-table site, I'm just going to click on atomic radius down here, and I actually get a good visual of the radii of each atom on the p-table, at least most of them. So again, the radius definition here says the size of atoms from the center of the nucleus to the outside. I just focus on it being the size of the atom, period. That's what I think about. Okay, we're never going to really do any math with the radii, so don't worry about the actual number. We just need to worry about the trend, like where are the big ones, where are the small atoms, and why is it happening that way? So what we can see here is that the big atoms tend to focus on the bottom left of the table. Cesium looks to be here the biggest out of all the calculated or measured ones. And the smaller atoms tend to be towards the top right. We're looking at you, helium. We're going to talk about helium a lot today. Woohoo! I love the helium. For the small atoms, top right. Big atoms, bottom left. If you didn't catch this from the other day, the reason why this happened. So the atoms get big going down the table because you are adding another energy level. So as you add another energy level, your atom gets bigger. Kind of like what's called a Russian nesting doll. Look that up if you want to. That's where there's like a doll in a doll in a doll in a doll. All right, you take off the top of a doll and there's another one in there, kind of like that. Or gobstoppers. It's a candy where you eat the candy and you get like another color after like a minute or so, and then there's like a crunch center in the middle. I don't know. It was just Halloween. So that's why they get bigger going down, but smaller going to the right. That was kind of weird because you would think adding more electrons into your atom would make it bigger, but adding another electron in your atom also adds another proton, and protons are all congested in the nucleus. So as you add more protons, let's say you're going from aluminum to silicon to phosphorus to sulfur to chlorine to argon, you're adding more proton, and that's increasing the pull towards the nucleus, those outer electrons. As you add more protons, the electrons just going to get closer to the middle. And that's why it gets smaller going to the right side. Again, some of you might be asking, what's the point looking at different sizes of atoms? Well, the sizes of the atoms explains why certain atoms are more reactive or less reactive, and why like carbon dioxide is what it is, why it's got one carbon and two oxygens, and why it's a certain size. Also, why helium, or one reason why helium is super unreactive, while sodium and potassium are super reactive, also deals with something else. So that's radius. Next one I want to look at is ionization energy, which is pretty much, I call it It's similar to like how easy it is to take candy from a baby. You can think of it that way. Um, Maybe, I don't know. Not taking something from somebody. If someone is holding on to something really tightly, it's hard to take it away. Okay. So a lot of times taking candy from a baby, you don't want to take the candy because then the kid cries and then the kid is crying and that's no good. And so it's hard to take candy from a baby. I would like to think of that as elements with high ionization energy. So on the P table, we're seeing kind of the opposite trend of radius. Radius was bigger bottom left and smaller top right. Well, eye energy is it's flipped. The largest ionization energy is actually helium. You'll see it's big in the top right of the table. That's where it tends to be the largest. The smallest energies tend to be the bottom left. Reasons, well, similar to the atomic size. The bigger your atom, the easier it is for an electron to just say, peace, I'm out, to flick an electron off the atom. You can think of it like it's easier to lose something in a big house like cesium. Cesium is one of the biggest atoms. So it's kind of like living in a mansion. Can you imagine if you lost like your earbuds and you lived in a mansion? Where are your earbuds? I don't know. You have like 50, 20, 30 rooms to look through. You're never going to find your earbuds. So it's so easy for an electron in cesium to just say peace, and it just flies off. Big atom. And it's really far away, this one electron. But helium or neon, their atoms are very small. Kind of like living in a really small house or a small apartment. If you lose your earbuds, it's easier to find them. It's easier to hold on to the things you cherish in a smaller house because it's a smaller place. It's easier to find things. You don't need as much stuff in a smaller house, so you kind of cherish what you have. Um, Same thing with these small atoms. All the electrons are close, so they're kind of a close knit group. There's no loners, right? In cesium, there's one outer electron. We'll show that a little later. And that one electron is so easily just peace, I'm out. But these smaller atoms, helium, neon, fluorine, chlorine, argon, oxygen, sulfur, they're so closely, tightly packed in there that it's hard for electrons to leave. Also, they don't want to leave. The reason why they don't want to leave. We'll get to that later today, too. Okay. Again, last one is electronegativity. So electronegativity is the tendency of an atom to attract electrons to itself. Pretty much attractiveness. So on the periodic table, there are certain atoms that are very attractive and certain atoms that are not attractive. All right. We'll see the trend also is the same as ionization energy. We'll see some of these atoms don't have electronegativity. That's fine. Fluorine and oxygen and chlorine and sulfur. So all these top right elements, again, have super high electronegativities. They tend to attract electrons. If you think about it, they're really small. So let's say you got a small atom and a nearby electron comes close to it. All of a sudden, it's going to be attracted because it's a smaller atom. So that extra electron is floating nearby. And all of a sudden, it attract because the atom is smaller, so it can be attracted more easily to that nucleus and to the atom. On the other hand, well, plus these atoms want electrons is the reason why. Talk about noble gases in a minute. Bigger atoms, I mean, they are larger, so the electrons that are nearby that it could steal are further away. So they can't get as close to the nucleus because they're further away. It's like a magnet. That's a lot of this stuff is basically based on magnets. So stronger magnets are like fluorine and chlorine because other atoms' electrons can get closer, and all of a sudden get closer, and so they steal them. Ah, gotcha. But francium, cesium, all these ones up here to the bottom left, they're bigger, bulkier atoms. So other electrons can't get close enough to that nucleus for the atom to steal it, right? And so this electronegativity is the basis of chemical reaction. Okay, this and also ionization energy, and they all kind of like when they all kind of work through this like chemical ballet. It all works together in order for reactions to happen, which is pretty cool. So what this all boils down to is that atoms want to be stable. They want to be happy. So make sure, again, all that stuff was those trends, just where it's biggest and smallest would be in your notes, or at least in the document. I want to focus on the actual periodic table. So in your notes, you don't have to draw the whole P table. Please don't. It takes much time. You can just draw like an outline of the P table, maybe with these groups. We are going to focus on eight primary groups of the P table. I'm actually not going to deal with the transition metals at all. Okay, because oops, I just screwed up. The transition metals are kind of weird. We'll deal with them eventually this year, but for the moment, transition metals just kind of screw everything up. They kind of screw up some trends, so we're going to forget about them. So we're going to focus on these 8 groups. So there's 1, there's 2, there's 3, 4, 5 is nitrogen group, 6, 7. These are the halogens, and then group 8. Ooh, group 8 is the most popular group on the periodic table, I think, the noble gases. These, get rid of that, there you go. These are actually the most stable elements on the periodic table. They're the most stable elements in the universe. Everyone wants to be like a noble gas. All right, everyone. So I usually like to think that the noble gases are like Michael Jordan. Like in the 90s, Michael Jordan was everything. Everything was Michael Jordan. He was all over the place. Everyone wanted to be like him. There's even a song, I Want to Be Like Mike. He's the greatest. Okay, there's no competition, at least in my mind. So back then, everyone wanted to be like him. There's only one MJ. So people tried to be like him. They made songs. They did all this stuff. They tried to play as good as him. They tried to beat his records and stuff or whatever. But no one was MJ. So on the P table, noble gases are like Michael Jordan. In order for other elements to be stable, like fluorine, oxygen, lithium, even hydrogen, or even magnesium, aluminum, all these other elements, in order for them to be completely 100% stable in a reaction, you have to become, in a way, they got to become like a noble gas. All right. Noble gases are very stable. Like I said before, you can inhale helium and be fine. You're not going to hurt yourself. You just inhale helium for a few seconds and then talk like I don't know, Mickey Mouse or something. Going to be fine. But sodium has to do something in order to become like its closest noble gas. If you take a look, sodium is very close to neon. It's actually 1 electron away. Beryllium is 2 electrons away from helium. So take a look. If beryllium loses 2 electrons, bam, bam, it becomes like helium. Good. So we'll get to this in just a minute. But what I want to list out on our P table in colors, I'm going to use blue for valence electrons. I'm going to use orange for the charge of the ion that is created when this element in this group forms an ion. All right, ions are like the basis of what we're dealing with the rest of the semester, all about ions and how certain atoms come together and how reactions occur. In your vocab that you just hopefully did, valence electrons are electrons on the outermost energy level. So they're the ones that are that if you were to look at them, you would see. I like to think of apples a lot. Okay, so when you go to the store and you pick out apples to buy, you look and see what they look like. You don't know what they look like on the inside. You see what they look like on the outside. Right. So if you want a Granny Smith apples, you look for the big green ones. If you want Honeycrisp, you look for ones that are red, yellow. They have that reddish yellow hue to them. Red Delicious, which I despise. Look for those blatantly red apples. So we're looking for the electrons on the outermost energy level. And so on our on your P table, so in your notes, above the group, we're going to put the number of valence electrons in that group, that atom. So you're going to see a trend. So let's do the trend then. Group 1, each atom has 1 valence electron. And I'll show you where that is in just a minute when I go to the P table site and we look at the electron tab. Group 2 elements, beryllium, magnesium, calcium, your alkaline earth metals, they have 2 valence electrons. We'll get to why in just a minute. And yes, the trend continues. So group 3, boron, aluminum, gallium, etc., they have 3 valence electrons. Group 4 elements, carbon, silicon, germanium, they have 4 valence electrons. Yes, you're right, the trend continues. Group 5 elements have 5 valence electrons. Group 6 elements have 6. Group 7 elements have 7. And group 8 elements have 8, with the exception of helium. Helium is only 2. So make sure you jot that down. Helium only has 2 electrons, so it can only have 2 on the outside maximum. You're asking yourself, how did this happen? How do we know that these atoms have this many valence electrons? Again, the ones on the outermost energy level. I want to take a look at our P table site. Let's go to the electrons tab. Let's just pick an element from group 1. So hydrogen, lithium, sodium, potassium. What we're noticing is that the highest energy level in potassium is level 4. No other 4s are filled up. For F, for D, for P, for S. Oh, there's 4S. 4. Oh, 1 electron. That's nice. Let's check sodium. Oh, sodium, 3. Oh, 1 electron and 3. Nothing in the 3, nothing. Okay. You're seeing a trend. Yay for trends. Rubidium. Check out rubidium. 1 electron in the 5 energy level. In the 5th, in the 5, in the 5th energy level. 1 electron. So we're seeing a trend. Group 1 atoms have 1 valence electron. Group 2 is similar. It's only got 2. You can check magnesium. It's got 2 electrons in the 3rd energy level. 3rd level is the highest for magnesium. Calcium, 4th energy level is the highest. It's got 2. Group 2. Interesting. And we keep going to the right, and you'll see that, yeah, the S's aren't there anymore, but check out the 2p for boron. Oops, there we go. So 2p for boron, there's 1 electron, but 2s has 2. So the 2nd energy level has 3 electrons in it. Check aluminum. The 3rd energy level has 3 electrons. Gallium, the 4th energy level has 3 electrons. You're going to see a trend constantly going to the right that you add an electron in the highest energy level. And those are valence electrons. So again, helium only has the 2. It's a weird kind of trend, but I guess not that weird. You're just adding an electron each time you go to the right. We're going to use that in the coming weeks when we start talking about how things bond together. Because again, everything wants to be like the noble gases. So the last thing we're going to deal with today, again, today's mostly note-taking for us. We'll get to more of this stuff next week. But I want to focus on the charge of the ion that's created when the atom in this group forms an ion. In your notes in your vocab you did before, ions are charged atoms from losing or gaining electrons. The reason they lose or gain is because they want to be like Mike. They want to be like these noble gases. So they're lazy. They're going to find the shortest, easiest path to become like the closest noble gas. All right. I'm going to check out group 1 atoms. For instance, sodium. So sodium, there's 2 noble gases that are close to it. First, you can go forward to argon. Oh, geez. That's adding 7 electrons to become like argon. Ugh. Or sodium can just lose 1 electron to become like neon. Huh. So for an atom, what's easier to do? Gain 7 of something or lose 1 of something? It's going to be whatever's lower. All right. It's easier to lose an electron, become like neon, than to gain 7 electrons to become like argon. This was too hard. It takes way too much time. Kind of like in gym class. Would you rather run 1 mile to get credit or 7 miles to get credit? It's the same credit. I'd run 1. Okay, because there's really no thought for atoms. They just do what makes them happiest, makes them what they do what's the laziest. So 1 mile is lazier than 7 miles. So the group 1 atoms are going to lose an electron. What happens is this makes them a positive 1 ion when they become an ion. If you're like, wait a second, you said they lost 1, shouldn't it be -1? Electrons are negative. So since electrons are negative, if they lose negativity, they become a positive charge. So if you as a human lose negativity, you become happier. You're going to see a trend with this also, but don't get ahead of yourself. Check yourself before you wreck yourself. Group 2 atoms are similar. Check out magnesium. Would rather lose 2 electrons, become like neon, than gain 6 to become like argon. Again, would you rather run 2 miles or 6 miles to get gym credit? 2 miles. So group 2 atoms lose 2 electrons to become a +2 charge when they form an ion. So like positive ions are cations, like a cat. Not cations, cations. All right, group 3s, you're right, they form a +3. Same thing, think about aluminum. Now we're getting closer to the weird things. Would aluminum rather lose 3 or gain 5? Neither. Or sorry, I'm stupid. It would rather lose 3. Again, 3 miles versus 5 miles get the same credit. What would an atom rather do? Lose 3. This is where the turning point happens in group 4, the carbon group. This is why carbon is the most popular element on the periodic table. If you think about carbon, would it rather lose 4 electrons to be like helium or gain 4 to be like neon? Well, in gym, would you rather run 4 miles to get credit or run 4 miles to get credit? You don't deal with charges in group 4 because it can be either or. This is where we get to the flip. So if you got ahead of yourself, make sure you check this out. Group 5, this is where again, things are different. Nitrogen. Would you rather lose 5 electrons to be like helium or gain 3 to be like neon? So again, this is the 3 or 5 mile discussion. You'd rather run 3 miles than 5. So nitrogen would rather 1, 2, 3 gain 3 electrons. It forms a -3 charge, gaining 3 electrons. Electrons are negative. 1, 2, 3. Yes, the trend is the same as we go. Oxygen group 6, they would rather gain 2 electrons to become stable, like a noble gas. And the fluorine group, the halogens, the most destructive non-metal group in the periodic table, they would gain 1 electron, become like a noble gas. And the noble gases, they're already like Michael Jordan, so they don't have to worry about trying to be like him. They already are. So the noble gases don't form ions because they're already stable. So they are already there. So make sure in your P table that you, or at least in your notes, you have these numbers and these charges because we're going to focus soon on how we can deal with valence electrons and how atoms bond and why they bond and how many atoms you need to make a certain bond. We'll figure that all out. Okay. Again, just keep in mind it's all about stability. All right. The most stable elements are the noble gases. So atoms throughout the P table are going to either lose or gain electrons to become like noble gases. This is why this all happens. So thanks for watching. Peace, everybody.